Welcome everyone to the Bootstrap workshop and school of this year. So as you know already, so the information and the schedule will be is available on the website of the Bootstrap collaboration. But most of the information, more detailed about recommended reading and the Zoom links, will be on the Slack channel. So if you know people that are interested in participating, them just invite them to join the Slack channel to have access to all the information. And in fact, we also encourage you to ask questions there and keep the discussion going in the Slack in case you don't have time to ask your question during the lectures. So today we had a last-minute change of schedule. So the talk of today at 5 p.m. in Europe will be by David Simons-Duffin. So we postponed the talk by Yi Chen He for July 15. So that's just information about that. Then what else do I want to say? Well, let me then go directly to the lecture today. So this year we have the privilege to begin the Bootstrap conference with the first lecture by Edward Witten on entanglement in quantum field theory. And we will try to have an informal attitude, so to allow questions in real time. So if you want, you can just use the raise hand tool of Zoom, or just unmute yourself and ask the question. Of course, if there will be too many questions at some point, we might ask you to postpone to the end or to Slack, but let's try like that in the beginning to have a more interactive ambience. And I think that's all. So Edward, please go ahead.
Well, thank you, Jill, and thanks to Slav also for the invitation. So my first two lectures will basically be about entanglement in quantum field theory. We'll then go on to other matters, starting with the third lecture. But here will be the list of topics of the first two lectures. I'll start with the Reeh-Schlieder theorem, which is the basic result showing that entanglement is everywhere in quantum field theory. Then we'll discuss relative entropy in quantum field theory, relative entropy in quantum mechanics. Then we'll do the density matrix for Rindler space, application to the Zamolchikov C theorem in 2 dimensions, and application to the Bekenstein bound. So those 6 are basically the topics of the first 2 lectures. So we consider a quantum field theory in Minkowski spacetime M, and the Hilbert space I'll call curly H, and it has a vacuum state omega. So such a theory has an algebra of local operators whose action can produce all states from the vacuum. Well, I put the word all in quotes because there might be super selection sectors. For example, in 3+1 dimensions, there could be electric and magnetic charges. So it might be that the local operators can only produce the states in a super selection sector. For simplicity in the notation, I'll assume that the algebra of local operators is generated by a single real scalar field phi, but that isn't important. That's just to keep the notation simple. So under these assumptions, states made by acting on the vacuum with a succession of phi fields are dense in the Hilbert space. Now, so that's kind of the basic idea of what quantum field theory means. Why do we have this Hilbert space? We have it because there were local operators that don't commute with each other, and realizing their algebra is what generated the Hilbert space. The Reeh-Schlieder theorem says that actually we get a dense set of states in the vacuum sector if we restrict the points x1 up to xn to any open set in M, no matter how small. So here I've drawn what you should imagine to be a small open set in Minkowski space. And the theorem says that if you simply consider your local operators inserted in this small open set, that's still enough to generate the Hilbert space. So I'm going to sketch how the proof goes. If the statement is false, there would be a state chi in the vacuum sector that would be orthogonal to everything we can make by local operators in U acting on the vacuum. And we'll show that such a chi actually satisfies the same condition without restricting the x's to be in the small subspace. But since states made by local operators acting on the vacuum are dense, this implies that chi is 0. So we'll define a function which is the matrix element between the vacuum state and chi of a product of local operators. We're given that this function vanishes if the xi are in the small open set U, and we want to prove it vanishes for all xi without that restriction. As a first step, we pick a future pointing time-like vector t, and we consider shifting xn by a real multiple of t. So U will be a real number. We shift the last point, the one closest to the vacuum, by a multiple of this vector t. So I've made the shift just on the operator that acts on the vacuum. And we define a function g of u that depends on u with all the other variables fixed. So we know that g of u is 0 for sufficiently small real u, because then xn plus ut is still in the set capital U. This is meant to be. Also, with h the Hamiltonian for translation in the t direction, we could write g of u as I've done here. And then, because h annihilates the vacuum, I can drop one factor here and write it like so. And the next step is that since h is non-negative, g of u is holomorphic in the upper half plane. So we have a function holomorphic in the upper half plane and vanishing in part of the real axis. Such a function is actually 0 by a simple application of the Cauchy integral theorem. If we knew g of u was holomorphic on the real axis and vanished on a segment of the real axis, we just say that g of u has a convergent Taylor series expansion around a point in the segment I, and this expansion would have to be identically 0 to make g of u vanish on the axis, but a holomorphic function with a vanishing Taylor series expansion is actually 0. To begin with, we only know that g of u is holomorphic above the real axis, not on it, but we can get around this using the Cauchy integral formula. So here's a point in the upper half plane where we know g is analytic. And now I've drawn a contour that runs around u, and we know we can reconstruct the function u from its values on that contour. Then I can move the contour so that part of it goes to the segment of the real axis where the function actually vanishes. So now I can represent the same function with a contour that goes around gamma and then heads back on the axis. But since the part on the axis is 0, the part of the Cauchy integral formula that contributes is just on this open contour. And that representation makes it obvious that the function is holomorphic if u is on the axis, and even in this representation, you can move u below the axis. See, in this representation, since we only have a partial contour, we could move u outside. And we learned that the function is identically, well, first of all, holomorphic everywhere, but therefore identically 0. So what we learned from that argument is that we could take the last point, xn, and shift it by a multiple of a time-like vector t without disturbing the vanishing. But now we do this again, picking another time-like vector t prime and replacing xn prime by xn double prime, where we've shifted xn prime by a real multiple of t prime. And repeating the argument, we learn that we still have vanishing for xn double prime here. But you can get anywhere in Minkowski space by starting at a fixed point and going forwards and backwards along time-like directions. So we actually learn that we have vanishing for any xn. So the first n minus 1 points are still in the small open set U, but there's no restriction on xn. The next step is to remove the restriction on xn minus 1. We do that in the same way. We use the same t as before. Now we make a common shift of xn minus 1 and xn in the t direction, like so. And we look at the shifted function h. It vanishes if u is small and real, and it can be written this way as before. we replace the shifts by ut by e to the iu times the Hamiltonian acting here and also acting on the vacuum, but we can drop that factor. And again, because the Hamiltonian is positive, we see that h of u is holomorphic in the upper half plane and vanishes on part of the real axis. So it's identically zero. Then we repeat the process by shifting xn minus 1 and xn in some other time-like direction. And finally, we learn that our correlator is zero with no restriction on the last two variables. The next step is to remove the restriction on the one before, xn minus 2. We do that in the same way by considering a shift of the last three coordinates by a common time-like vector, and so on. So after n of these steps, well, n zigzags, the next step would be a zigzag of the last 3 points, then a zigzag of the last 4, and finally we would do a zigzag of all n points together. After doing n zigzags, we end up proving that this function vanishes with no restriction at all on the axis. And therefore we learned that chi must be zero. So we end up proving the Reeh-Schlieder theorem. An arbitrary state, more exactly a dense set of states in the vacuum sector of Hilbert space, can be created from the vacuum by acting with a product of local operators in a small open set in Minkowski space. So now I want to discuss the interpretation of this theorem. So it sounds unintuitive at first, and you might think it contradicts causality. Consider a state of the universe that on some initial time slice looks like the vacuum near you, but contains the planet Jupiter in a distant region V, space-like separated from you. Let J be a Jupiter operator whose expectation value in a state that contains the planet Jupiter is close to 1, while its expectation value is close to 0 if the planet Jupiter is absent. The Reeh-Schlieder theorem says there's an operator x in region U, such that x acting on the vacuum creates the planet Jupiter in region V. So that means the vacuum expectation value of the Jupiter operator is close to 0. But in the state x on the vacuum, its expectation value is close to 1, because the planet Jupiter is almost definitely present in region V. Is there a contradiction? Well, we can rewrite this matrix element that's 1 in the form I've done here. And then x was supported in U, and we can assume J acts only in the space-like separated region V. So x dagger and J commute. So we could say that 1 is the vacuum expectation value of J times x dagger x. Now, so we have two statements. The vacuum expectation value of J is 0, but the vacuum expectation value of Jx dagger x is 1. If x were unitary, this would be a contradiction, because if x were unitary, then x dagger x would be 1. And there would be an obvious contradiction between these two statements. But the Reeh-Schlieder theorem doesn't tell us that we can pick x to be unitary. It just tells us there's some x in region U that will create the planet Jupiter in its distant region V. So all we really learn from the second formula is that in the vacuum, the operators J and x dagger x have a non-zero correlator, which is a connected correlator because the vacuum expectation value of J was 0. So we have a connected correlator between two operators at space-like separation. But there's no contradiction there, where more or less all operators in quantum field theory have space-like correlators with other operators. So there's no contradiction with causality. Instead, the Reeh-Schlieder theorem has the following intuitive interpretation. The interpretation involves entanglement between degrees of freedom inside the open set U and those outside U. To explain the intuitive picture, imagine that the Hilbert space H of our quantum field theory has a factorization as a tensor product of two factors, where HU describes the physics in U, and HU prime describes all the degrees of freedom. I wrote outside of U, but I should have written space-like separated from U. So this factorization is slightly oversimplified in quantum field theory. It would be true in a lattice theory. In a lattice regulated theory, we actually would have such a tensor to product decomposition. We take all the lattice points in U and all these space-like separate, imagine a Hamiltonian lattice theory. So we think of U as being a subset of the initial value surface, or the open set would be the domain of dependence of a portion of the initial value surface. Then HU would be the Hilbert space of all the lattices in our region, and HU prime would be the Hilbert space of all lattices outside our region. So morally, we can imagine such a decomposition, although technically in a continuum theory, it's not quite true. But anyway, let's proceed. Imagining such a decomposition. If you have such a tensor product decomposition, then any state in the Hilbert space, such as the vacuum, would have a decomposition as a sum of tensor products of vectors in HU and vectors in HU prime. And moreover, we can make this decomposition in such a way that the states psi iu are orthogonal to each other, and also the states psi iu prime are orthogonal to each other. And we can also assume that pi are positive. By rotating the phases of the states, we can make the square root of pi real, sorry, non-negative, let's say. But if pi were 0, we would just drop that term from the sum. So we can write such a formula where the pi are all strictly positive. So in general, whenever you have such a tensor product decomposition of a Hilbert space, any vector has such a decomposition with positive pi. Now, in general, in such a decomposition, the psi's and also the psi u primes are not a basis of their Hilbert spaces because there aren't enough of them. We can assume they're orthonormal, but they might not be enough of them to be a complete basis of either Hilbert space. However, something like the Reeh-Schlieder theorem is true for any state omega such that the psi I and the psi I prime do form bases of their respective spaces. I'm wondering how good Zoom is at suppressing background noise. There's a lot of noise outside my window. I'm going to shut it.
Thank you. It was working okay, but.
Okay. Well, if the noise wasn't bothering you, I'm impressed with Zoom's capability to avoid background noise. So using the fact that the psi I are a basis of HU prime, we would argue as follows. So I want to prove that something like the Reeh-Schlieder theorem is true, provided these states are bases of their Hilbert spaces. So if the psi I of U prime are a basis, then any psi has such an expansion with some lambdas in HU. But because the psi iu are a basis and the pi are non-zero, we can define a linear operator x acting on HU by this formula. And we see we found an operator x acting only on degrees of freedom in U, such that x maps omega into psi. So something like the Reeh-Schlieder theorem is true whenever the states that appear in this decomposition are a complete basis of each Hilbert space. One point I want to mention, what I've said is strictly true in finite dimensions. In infinite dimensions, because most of the pi are very small, the operator x we're defining here is an unbounded operator, which means that it only acts on a dense subset of Hilbert space, not on all Hilbert space states. And that goes with the fact that the Reeh-Schlieder theorem only proved that we got a dense subset of states in Hilbert space. We didn't literally prove we could get every state. We only proved we could get a dense subspace. And we see that from this version of the explanation of what the theorem means. With most of the pi being, with the pi tending to 0 in such a way that the state omega is normalizable, such an x would not be well defined on all Hilbert space states, only on a dense subset. So a state like this, where all the pi are positive and the psi I and u and psi iu prime are bases, might be called a fully entangled state. I don't think this is standard terminology. We call a state maximally entangled, that is standard terminology, if the pi are all equal. That's not possible for Hilbert spaces of infinite dimension, as in quantum field theory, although it's an important case for finite dimensional Hilbert spaces. The Reeh-Schlieder theorem intuitively means that the vacuum state omega of a quantum field theory is fully entangled between the inside and outside of an arbitrary open set U.
Can I just ask a
Yes.
short question? So this, when we do this decomposition in finite dimensional, this will work if both have the same dimension, right? You need the same.
Well, it works for all states. Any state has such a decomposition.
But H and H prime should have the same dimensionality.
No. Any state in a tensor product always has such a decomposition. If the dimensionality are not equal, then it's not possible for both sets to be a complete basis of HU or HU prime.
Right.
But such a decomposition always exists. You could think, good.
No, I was going to ask a second question. Please continue.
Well, think of if you have two Hilbert spaces, think of a vector in the tensor product as a matrix, where one index represents the first factor, the other index represents the second. You can always diagonalize the matrix, which is what we're doing here. But if it's a rectangular matrix, after you diagonalize it, there are some rows or columns of zeros. So the only thing which is special when the two factors have the same dimension is that you have a square matrix, which when you diagonalize it might have all non-zero entries on the diagonal.
So, but then it would not, if it's rectangular, this Reeh-Schlieder theorem will not apply, right? Because you could not generate everything.
It would not have an analog. So the Reeh-Schlieder theorem tells us, if you want to make the finite dimensional story, in Hilbert quantum field theory, the dimensions are infinite. And technically, this tensor product decomposition isn't quite valid, as we'll discuss. But in the Reeh-Schlieder analog in finite dimensions is only possible when the Hilbert spaces have the same dimension.
So yeah, I had a related question. You mentioned lattice. Is there a version of the theorem in a lattice theory?
Well, I don't. You can formulate it. There isn't a known version of the theorem in a lattice theory.
If you could perhaps diagnose,
obviously for spin systems, there can't be, because a spin system with a finite number of sites would have a finite dimensional Hilbert space. Yeah. And as we just discussed, if the two Hilbert spaces have unequal dimension, the theorem can't hold. If you put phi-4 theory on a lattice, it's not completely obvious there couldn't be such a theorem, but there's no such theorem I'm aware of. Obviously, the proof I gave wouldn't work because the proof used relativity, because the idea of shifting in different time-like directions wouldn't apply in a lattice theory. In a lattice theory, at most, we'd have one time-like direction we could shift in, and we wouldn't be able to make this argument. So,
okay, perhaps we could imagine like two diagonal symmetries, two Hamiltonians along the diagonals, but okay.
Well, lattice theories don't normally have that property. You can have a sort of light cone lattice theory, a continuum in 2 dimensions and latticized in the transverse dimensions. I still think you wouldn't get the theorem because you wouldn't be able to shift from one latticite to another. I think it's hard to imitate this theorem except in a relativistic theory. Are there questions from anybody else?
Well, what if the lattice theory has an infinite number of points? Still an infinite Hilbert space.
Well, you can make for phi-4 theory on an infinite lattice, or for spin systems where both U and U prime are infinite regions. There's no trivial contradiction with having such a fact hold, but I also don't know how the proof would go. It's conceivable that such a thing holds for some lattice theories. Any other questions? So the decomposition, the tensor product decomposition of the Hilbert space that I assumed in trying to give an intuitive explanation of what the theorem means is not literally valid in quantum field theory. If it were, the Hilbert space would contain unentangled pure states, psi tensor chi, where psi is in one factor and chi is in the other. But that contradicts the fact that in quantum field theory, there's a universal ultraviolet divergence in the entanglement entropy. So I will define entanglement entropy a little bit later. So in this sentence, I'm sort of rushing ahead of the logic of the talk. But as we'll discuss, there's this concept called entanglement entropy. And in quantum field theory, it's not possible to have an unentangled state such as psi tensor chi. So what we did assume to give an intuitive explanation of what the Reeh-Schlieder theorem means made sense in a lattice cutoff version of the theory, but wasn't literally valid in the continuum. So in a little while, I'm going to explain a sort of slightly more abstract formulation that lets you make rigorous statements about entanglement in quantum field theory. But first, we're going to discuss an important corollary of the Reeh-Schlieder theorem. So here I'll let U and V be space-like separated open sets in Minkowski spacetime. And B will be an operator supported in V. Suppose B annihilates the vacuum. Then, if A is supported in U, you see B acting on A times the vacuum is the same as A acting on B times the vacuum, because A and B commute since U and V are space-like separated. But B annihilated the vacuum, so the right-hand side is 0. So therefore, B annihilates A times the vacuum. But we proved in the Reeh-Schlieder theorem that the states A on the vacuum are dense in the Hilbert space, so B identically vanishes. So we've learned that if B is supported in a space like open set V that's small enough that it's space-like separated from another set U, then B can't annihilate the vacuum. The roles of U and V were symmetrical, so also if A is supported in U, it can't annihilate the vacuum. So we've learned that the vacuum can't be annihilated by any operator that lives in a set of space-time that's small enough that it's space-like separated from some open set. So let AU be the algebra of operators in region U. So I won't be very precise about what we mean by the algebra of operators, but somehow we take local field operators and make them into an algebra. Maybe we smear them and construct bounded functions of our smeared local field operators. And eventually we make them into an algebra of local observables. We've proved two facts about the algebra of a local region acting in the vacuum sector. One, the original statement of the Reeh-Schlieder theorem was that states of the form A on the vacuum where A is in the algebra are dense in the Hilbert space. That's described by saying that omega is a cyclic vector for the algebra A sub U. The second fact we proved, the corollary of the Reeh-Schlieder theorem, is that if A is in the algebra, it doesn't annihilate the vacuum. That's described by saying that omega is a separating vector for AU. So in short, the Reeh-Schlieder theorem and its corollary say that the vacuum is cyclic on separating. It's a cyclic separating vector for A sub U. And there, U is any open set in spacetime. Now we're going to go back to practicing with tensor product Hilbert spaces. So let H be H1 tensor H2, and A the algebra of operators on H1. Any vector would have a decomposition like I wrote before, which you can think of as resulting from diagonalizing a rectangular matrix. As I said, you sort of think of a vector in H1 as a column vector, the vector in H2 is a row vector. So the tensor product is a Hilbert space of matrices, rectangular matrices. Then by diagonalizing a rectangular matrix, you get what's called the Schmidt decomposition that we used before. And a reasoning similar to what I showed when I explained the intuitive meaning of Reeh-Schlieder is that a vector psi is cyclic for A if these vectors psi2i are basis for H2. It's separating for A if the psi1i are a basis for H1. So for example, to prove that it's what would it mean for psi to be separating for the algebra A? If I act with an element of curly A, which means an operator that acts on the first factor, to annihilate this state, would have to annihilate all the psi1 i's, because their coefficients are linearly independent vectors psi2i in the second Hilbert space. So if you want to know that psi isn't annihilated by any operator in curly A, there should be enough psi1 i's that they're a basis for H1. And by similar logic, psi is cyclic for A if the psi2 i's are a basis for H2. So the cyclic separating property just means that the psi1 i's and likewise the psi2 i's are each bases of their own Hilbert spaces. So the Reeh-Schlieder theorem and its corollary corresponds to something like this in the case of quantum field theory, where the two factors refer to any region and whatever is space-like separated from it. So that completes the discussion of the first topic, which was the Reeh-Schlieder theorem. The remarks I made interpreting the theorem were, in terms of entanglement, were only heuristic, because there's not really a factorization of the Hilbert space in quantum field theory. A mathematical machinery that can be useful to make rigorous statements when the Hilbert space doesn't factorize is called Tomita-Takesaki theory. It applies whenever you have an algebra A acting on a Hilbert space H with a cyclic separating vector. So the Reeh-Schlieder theorem provides precisely the input needed in Tomita-Takesaki theory. So my second topic is an introduction to this. The starting point in Tomita-Takesaki theory, well, given an algebra A with cyclic separating vector psi, we define an antilinear operator called the Tomita operator. I'll call it S sub psi. It maps H to H. It's defined as follows. Acting on a vector A psi, S psi will produce A dagger psi. The definition makes sense because of the separating property. If we could have had A psi equals 0 with A dagger psi non-zero, the definition would lead to a contradiction. But we've proved that there's no element of the algebra that annihilates the vacuum. So therefore, the definition is consistent. And it defines S psi on a dense set of states in Hilbert space because of the cyclic property. The cyclic property says that states A psi are dense in H. So we've defined this operator on a dense subset of Hilbert space. The definition can't be extended to all of Hilbert space because S psi is an unbounded operator. That happens because although we prove that A psi can't be 0, it can be extremely small. To try to make that obvious, take our local region. And a mode that's trying to lower the frequency, a negative frequency mode, would annihilate the vacuum, but it's impossible to have a truly negative frequency mode in a bounded region. But by taking a mode of very high frequency, you can come very close to having pure negative frequency or pure positive frequency in a bounded region. So you can't make A psi 0, but you can make it very small. And if A is almost an annihilation operator, then A dagger is almost a creation operator. So S psi is unbounded because it can map a very small state to a very large state. As an unbounded operator, it won't be defined on all of Hilbert space, but we did define it on a dense set. Well, one fact obvious from the definition is that S psi squared is 1. If you iterate this definition, you learn that S on A dagger psi has to be A psi, so S squared is 1. Another fact is that S psi in the vacuum is the vacuum, or S psi in psi is psi, whatever psi is, because psi is just 1 times psi. If I set A equals 1, I learned that S psi on psi is psi. So the modular operator is the linear self-adjoint operator defined by S dagger delta equals S dagger S. So I use here the notion of the adjoint of an antilinear operator. The definition is here. So delta psi is positive definite because S psi was invertible, which we know because S psi squared was 1. Now, for an application I want to explain, we also need something called the relative modular operator. So let psi be a cyclic separating state and phi any other state. The relative Tomita operator S psi phi is an antilinear operator defined like so. I have to warn you that what I call S psi phi, a lot of authors reverse the orders of the two states phi and psi in this definition. I write it this way because I think it makes some formulas look more natural. So again, the well-definedness of the definition depends on psi being cyclic separating, but no property is needed for phi. We don't lose anything essential if we assume that psi and phi are unit vectors. Then we define the relative modular operator as S dagger S. It's still self-adjoint and positive semi-definite, but it's not necessarily invertible. If phi equals psi, because previously we had S squared equals 1, but once the two states are different, we no longer have S squared equals 1, and delta might not be invertible. If phi equals psi, the definition is reduced to the previous ones.
Can I ask a question?
Yes, please. Go ahead.
Yeah, so in rigorous theory, one usually suffers a lot to prove that some operators which look self-adjoint are actually self-adjoint in mathematical sense. So for this Tomita, for this delta phi operator, delta psi operator, is it to show that it's actually self-adjoint as opposed to just looking densely defined symmetric operator?
There are some points where there are tricky analytical details. If you want to read about it, there are lots of not very. There's a source I recommend for learning about such things. Vaughan Jones has some excellent lecture notes that you can find online. I don't think they're ever published, but they're easy to find online. Just look for Vaughan Jones lectures on von Neumann algebras or some such title.
Okay, sounds good.
There is one tricky point. In my lecture notes, there's a footnote where I mentioned the trickiest point here. I don't think it's exactly what you asked about, but it's something similar.
Okay.
Any other questions? I think if I take your question literally for S dagger S, there isn't a problem, but there are some statements, there are some simple statements here that actually require tricky analytical proofs. So now we're ready to define relative entropy in quantum field theory. The definition is simple. The problem is more to explain, to give you some intuition about what it means. That'll take a while extended over the first two lectures, but the definition is an easy one. We fix an open set U, small enough so the vacuum is cyclic separating. That just means that there's some other space-like separated open set. And we consider the algebra A sub U. We let psi be any cyclic separating vector for A sub U, but often we'll take psi to be the vacuum, and phi is any other vector. The relative entropy between the states psi and phi for measurements in the region U was defined by Araki by this formula. The expectation value in the state psi of minus the log of delta psi phi. So, today and tomorrow, I'll say various things that will hopefully help you understand why this is a good definition. But for now, we just make this definition. So first, I'm going to discuss positivity properties that are actually easy to prove. First of all,
just a small question. I should interpret this as the relative entropy with respect to the subalgebra U, correct? On U? Okay.
Yeah, the way I said it was, I think, the relative entropy for measurements in region U.
Okay, great, thank you.
Any other questions? So if phi equals psi, we know that delta psi on psi is psi. So log of delta psi of psi is 0. So the relative entropy between psi and itself is 0. Just because if phi equals psi, this operator is 0. Sorry, not 0. It's not 0, but it annihilates psi. Now consider a completely general state phi. For a positive real number lambda, there's a simple inequality that minus log lambda is equal to or bigger than 1 minus lambda. You can prove it by, I think, seeing that they're tangent at lambda equals 1, and one has a positive second derivative, the other vanishing second derivative. So therefore, for operators, minus log delta is equal to or bigger than 1 minus delta. And using that inequality in the definition of relative entropy, so we get an inequality by replacing minus log delta with 1 minus delta. And once we replace it with 1 minus delta, we can evaluate it from the definitions. One term is the inner product of psi with itself. The other is the expectation value in the state psi of S dagger S. And by the definition of S, that's the inner product of phi with itself. But we assume both states were normalized, so the difference of expectation of normalizations is 1 minus 1 or 0. So we've proved that in general, the relative entropy with Araki's definition is non-negative. Now, some of you will have previously seen a definition of relative entropy for a general quantum system without necessarily using this fancy story about the modular operator. Later I think means tomorrow, but later we'll discuss how the definition that's often given compares to what I've said. But we're going to move on to an important fact about relative entropy, which it actually has the unusual property that I think it's easier to understand it in quantum field theory than it is in a finite dimensional quantum system. That's actually why that's one reason I started with quantum field theory rather than the finite dimensional quantum system. So we have an open set U, and we're going to consider a smaller open set U tilde. So now we have two different algebras, AU and AU tilde, and therefore there are two different relative modular operators for the two regions. So we could look at the Tomita operator S psi phi for region U tilde or for region U, and likewise there are two modular operators delta psi phi for the smaller or bigger region. So the relative entropy for measurements in region U is what we've discussed a little bit. And if I just replace U by U tilde, I get the relative entropy for measurements in region U tilde. We want to prove that relative entropy is monotonic under increasing the region considered. That's important for all kinds of applications. I'll be explaining two applications where this is important, which will be the C theorem in 2 dimensions and the generalized second law of thermodynamics. There really are all kinds of applications. But, well, I'll manage to explain 2 of them in these lectures. So in explaining why this is true, we're going to hold the states psi and phi fixed. So to lighten the notation, we'll omit some subscripts and denote the operators as just SU, SU tilde, and likewise delta U and delta U tilde. The main point of the proof is to show that as an operator, delta U tilde is equal to or bigger than delta U. That means in any state, the expectation value of the left is bigger than the expectation value of the right. I'll explain in a moment that that implies that log delta U tilde is not less than log delta U. So the inequality we want for monotonicity of relative entropy is just a matrix element of this inequality in the state psi. So to prove monotonicity of relative entropy in this formulation, we just need to know that this statement implies this statement, which of course would be true for numbers, but we need to prove it for operators. So we want to show that if P and Q are positive self-adjoint operators and P is equal to bigger than Q, then log P is equal to bigger than log Q. We can let R be a convex linear combination of P and Q, where T is between 0 and 1. So R is an increasing function of T because R dot is P minus Q, which is non-negative. And then we have this nice formula for log R. So that's true for matrices because it's true, operators because it's true for numbers. You can imagine diagonalizing R, and then this would reduce to a statement for each eigenvalue. So d by t of log R has this formula. And the integrand is positive because it's BAB with positive operators. A is R dot and B is 1 over S plus R. So even before integrating, this is positive, and therefore the integral is positive. So we've proved that if P is bigger than Q, then log P is bigger than log Q. And that's the last step we needed to prove monotonicity of relative entropy.
Sorry, I got a bit confused with the logic of this proof because, I mean, if we can use the fact that we diagonalize, wouldn't it just follow like the way it follows for numbers? That P greater than...
No, because you can't simultaneously diagonalize P and Q. So to compare, you see, if you could simultaneously diagonalize P and Q, then it's true that this statement for operators would follow from this statement for numbers. But because you can't simultaneously diagonalize them, you can't make a trivial argument like that. We avoided talking about more than one operator by looking at a linear combination of P and Q.
Ah, I see. Okay.
And then now we only have a single operator, R of T, so we can diagonalize it. And therefore, this step was true for operators because it's true for numbers. When we differentiate with respect to time, that's tricky because R and R dot don't commute. So the formula I wrote here for the time derivative of this integral is true, but it might take you a little thought to check it. Because since R dot and R don't commute, the operator ordering here is crucial. And you have to check that I've ordered the factors correctly so that the time derivative of this actually is this.
I see. Thanks.
I think if you try to think it through, you'll be able to see that it's true, but it's the step going from this one, sorry, the step going from here, step going from this formula to this formula isn't completely trivial because the non-trivial step was the way you order operators when you differentiate -1 over S plus R. But I realize that to some of you, it might seem that what we proved is trivial. So in the next slide, I'm going to tell you something fun. In case you think we proved something obvious, let me remark that for operators, the inequality P bigger than Q does not imply P squared bigger than Q squared. It's actually false for 2 by 2 matrices. I think I gave a counterexample in my lecture notes, which were recommended reading. So you could look up the counterexample somewhere in section 3 of those notes. The function P going to log P is better. So we proved that P being bigger than Q implies log P bigger than log Q, but it doesn't imply that P squared is bigger than Q squared. But in the other direction, if P squared is bigger than Q squared, then P is bigger than Q. So these statements, when they're true, at least the statements I know about that are true, have relatively simple proofs, similar to this one. But a lot of plausible looking statements are not true. So, okay, so we only need to know one more thing to prove monotonicity of relative entropy. If we can prove that delta U tilde is bigger than delta U, then it'll follow that log of delta U tilde is bigger than log of delta U. And then our inequality that we want is just a matrix element of that. So we only have to prove this. Now, if we try to understand this inequality, we might get confused at first. So the deltas were defined in terms of the Tomita operators. And naively, the two S's were defined by the same formula, with the sole difference that in one case, A is in one algebra, and in the other case, A is in a larger algebra. So the algebra AU is bigger, so SU is defined on more states. But the states in which the states in the smaller algebra already give a dense subset of Hilbert space. So SU tilde and SU actually coincide on a dense set of states. Now, if you're too careless, you might assume that operators that agree on a dense subspace of Hilbert space are actually the same. But that's not true for unbounded operators. We have to remember that an unbounded operator is never defined on all states, only at most on a dense subspace. The proper statement is that SU is an extension of SU tilde, meaning SU is defined whenever SU tilde is defined, and when they're both defined, they agree. So in our problem, SU is a proper extension because the algebra AU is strictly bigger than the algebra AU tilde. They're operators that live in the larger region but don't live in the smaller region. So there are states you can make by one that you can't make by the other. So SU is defined on more states than SU tilde. So the fact that SU is an extension of SU tilde implies as a general Hilbert space statement that S dagger S is bigger for the S that's defined on fewer states. And that's what we need for monotonicity of relative entropy. The intuitive idea of the inequality is that the fact that SU tilde is defined on fewer states than SU corresponds to a constraint that's been placed on the states in the case of SU tilde. And this constraint raises the energy. In other words, if we think of delta as a Hamiltonian, then allowing delta to act on fewer states means that you've put a constraint on the wave function. A way to impose that constraint would be to remove some states from the Hilbert space by adding a term to the Hamiltonian that makes them go to very high energies. And that'll raise the energy of the remaining states. So this operator will be bigger than this one precisely because it acts on a smaller subspace of states. I'm going to give an analogy that tries to make this more intuitive. Instead of SU, we're going to consider the exterior derivative D that maps functions or zero forms on a manifold to one forms. But we'll assume that the manifold has a boundary N, and we'll consider two different versions of the operator D. One will be, I'll call it D hat. It's the operator acting on differentiable functions that vanish on the boundary. We'll also consider the same operator without the constraint that the function vanishes on the boundary. Differentiable function, you can make a Hilbert space from functions, and differentiable functions that vanish on the boundary are dense in Hilbert space. So D hat and D are each defined on a dense subspace of Hilbert space. Moreover, obviously, D is an extension of D hat because it's defined whenever D hat is defined, and they agree when they're both defined. Now, we're thinking of D and D hat as being analogous to the Tomita operator. So the analog of the modular operator would be the Dirichlet-Laplacian D dagger D. So we can associate Laplacians to both D and D hat. But D hat is associated to the Dirichlet-Laplacian because we constrain the wave function to vanish on the boundary. But D is related to the Neumann-Laplacian without that constraint. So the Neumann and Dirichlet-Laplacian are non-negative operators, and they coincide on any state that vanishes near the boundary, which is a dense set of states. But delta hat is more positive than delta because of the constraint that the wave function should vanish on the boundary. So the Neumann-Laplacian is associated to an energy function that probably is familiar from scalar field theory. But to get the Dirichlet-Laplacian, we should add a boundary term to the energy to make the wave function vanish on the boundary. So we can consider a family of operators where we add a boundary term to the energy function. At t equals 0, we would have the Neumann-Laplacian. At t equals infinity, we would get the Dirichlet-Laplacian because we'd get a constraint that f should vanish on the boundary. Clearly, the energy is an increasing function of t because we're just adding a positive t-dependent term to the energy function. So Therefore, the Dirichlet-Laplacian at t equals infinity is more positive than the Neumann-Laplacian at t equals 0. So the Dirichlet-Laplacian is bigger than the Neumann-Laplacian, which is analogous to our desired inequality that the modular operator for the smaller region is bigger than the modular operator for the bigger region. We're saying simply that a constraint on the state always raises the energy. Just to repeat the analogy, delta U tilde is the operator associated to the energy function for a state in the domain of SU tilde. Delta U is similarly associated, well, is the energy function for a state in the larger domain of SU. The two energy functions are the same, except the second is defined on the larger set of states. We can get the second from the first. We can get the first from the second by a constraint that removes some states. It's written backwards here. A constraint that removes some states can only raise the energy, so one Laplacian is bigger than the other. Now, what I tried to do instead of showing you the precise proof is to try to explain the result. If you look at section 3.6 of my notes, you can see a precise version of the proof. So that completes what I'm going to say about the second topic of my lecture, which was about Tomita-Takesaki theory. I've explained what I regard as the most transparent explanation of monotonicity of relative entropy. The argument as stated only applies to the special case of increasing the size of a region in spacetime. But we can consider a general quantum system, finite dimensional for simplicity, and imitate some of the ideas. So I think this will involve going on for about 10 more minutes. Is that reasonable with the time?
Yes, we are quite flexible with time.
Okay, so we're going to consider a finite dimensional quantum system and imitate what we've done. We'll define the Tomita-Takesaki operators and compare our definition of relative entropy to the one that you might have seen before. And then we'll give a physical proof of monotonicity of relative entropy in general. We might not quite do all of that today. We'll see what we can do in 10 minutes. As background, I want to first review the basic idea of a density matrix. So we start with a pure state psi AB in a tensor product Hilbert space, HA tensor HB. And first we make the pure state density matrix, which is just the projection operator onto psi. I assume that psi is a normalized state. I didn't write that. The expectation value of any operator in the state psi is the same as the trace of the operator times the density matrix. To prove that the left equals the right, you basically just take the bra from this formula, move it over to the right to make the density matrix rho, and then taking the trace undoes that. Now, assuming that psi was normalized, rho AB is the orthogonal projection operator on the state psi. In particular, its Hermitian non-negative and its trace is 1, and it has rank 1. But suppose we're only going to observe the subsystem A. That means we only consider operators of the form OA tensored 1 acting on system B. The expectation value of this operator in the state psi AB, well, it's the same as before, but I replace OAB with OA tensor 1B. But now, since to do the trace, we have to sum over all states in A and over all states in B. But the trace over the B part is easy because the operator acting on B was the identity. So we define what's called the reduced density matrix of system A by taking the trace over B of rho AB. That means roughly that you sum over all states of the B system. You take a matrix element of rho AB, but on the index that acts on the B system, you sum over all possible diagonal matrix elements. You take what's called a partial trace over B to get rho A from rho AB. So this formula shows that if we're only going to make a measurement on the A system, we don't need row AB. We only need row A because we were able to write the probability, the expectation value of an operator that only acts on the A system in terms of this reduced matrix that only acts on A. The definition of row A ensures that it's Hermitian non-negative and has trace 1, just like row AB, but it does not necessarily have rank 1. We lose the rank 1 property because of summing over the indices of system B. If psi AB is an entangled state of the subsystems A and B, then row A has rank greater than 1. An entangled state is just any state that's not a tensor product of separate states of the two subsystems. So almost every quantum state of the combined system is entangled. An important notion about density matrices is purification. If psi AB is a bipartite pure state with density matrix row A on system A, we say that psi AB is a purification of row A, row A. Every density matrix has a purification. Remember, row A density matrix is always going to be a Hermitian non-negative matrix. So it can always be diagonalized and written like so with positive coefficient CK. For purification, we can take the pure state that I've written here, where I introduce some other Hilbert space of the same dimension, and K prime or orthogonal states in the other Hilbert space. So this pure state has the property that its purification will give us the density matrix rho. Now, before getting to relative entropy, let's discuss the meaning of entropy at the quantum level. Entropy in microphysics was originally defined by Boltzmann in the 19th century. So he considered a system of n particles in a box with positions x and momenta p. As a classical physicist, Boltzmann assumed that at a given time, x and p have definite values, even if we don't know them. He described the state of our knowledge by a probability distribution function rho that encodes our knowledge. And after great labor, he arrived at a definition of the entropy as a phase space integral of minus rho log rho. For a quantum system, the density matrix rho, which we introduced a moment ago, is the closest analog of the classical probability distribution function. Recall that if a system has density matrix rho, the expectation value of any observable is the trace of O times rho. If we diagonalize the density matrix with eigenvalues lambda j, the expectation value of O is the sum of lambda I times the diagonal matrix elements of O, as if the system is in state I with probability lambda I. That interpretation makes sense because rho is non-negative and has trace 1. So the lambda I are non-negative and their sum is 1. So the quantum analog of Boltzmann's integral is the von Neumann entropy of a density matrix. In the classical limit, von Neumann's definition goes over to Boltzmann's. If the eigenvalues of rho are lambda 1 up to lambda n, then S can be written as a sum of minus lambda log lambda. So what are the basic properties of S? Well, if the state of a system is known with certainty if one of the lambdas is 1 and the others are 0, which means that rho has rank 1. In that case, the formula for entropy gives 0. Otherwise, every non-zero lambda makes a positive contribution, so S is positive. If a system is entangled with something else, then rho has rank greater than 1, and therefore S is strictly positive. There's a fundamental difference between the classical and quantum cases that has to do with entanglement. Classically, one assumes x and p have actual values, and one uses a distribution function rho because of lack of microscopic knowledge. Quantum mechanically, a system can have a fine-grained or microscopic entropy, even if we have as full a description of its state as quantum mechanics allows. That happens because of entanglement. Suppose A and B are two quantum systems in an overall pure state psi AB. If psi AB is entangled, the density matrix rho A of system A by itself has rank greater than 1, and the system A has a positive von Neumann entropy. if A and B are entangled, you can verify this experimentally, and there's no way to describe system A by a pure state density matrix with zero entropy. In general, just as classically, our knowledge of the state might be less complete than quantum mechanics allows. In that case, we describe a system by a density matrix rho that reflects our knowledge. For example, if we know nothing about the state of a system, we take rho to be a multiple of the identity, even though someone else who knows how it was prepared might describe it by a pure state. If we only know a temperature, we describe a system by a thermal density matrix. In such a case, the von Neumann entropy is the thermodynamic entropy, a familiar classical concept. But to reiterate, what's different about quantum mechanics is the entropy that remains if our knowledge is as complete as quantum mechanics allows. It's been called entanglement entropy, and it's also been called fine-grained entropy. Now, sorry, let me remember. Okay, I think I'm just going to explain this one slide here. And then I'll stop. The definition of relative entropy in a general quantum system is similar to the definition of the von Neumann entropy. So remember, the von Neumann entropy of rho was minus trace of rho log rho, but the relative entropy is defined, well, one term is minus the entropy of rho, and you add another term with log sigma. Again, it's easier to give the definition than to explain why it's a useful definition. But next time we'll make contact between this definition and the definition I gave in quantum field theory, and that will help us understand why this is a good definition. And then we'll explain various applications. As I said, one will involve the C theorem, one will involve the generalized second law of thermodynamics. For today, I'll just conclude by proving directly from this more elementary definition something that we proved earlier using Iraqi's definition. Namely, that relative entropy is non-negative and is strictly positive if rho is not equal to sigma. So I'll give a short proof of that just using this formula. So we use the same trick as we did in one other proof. We interpolate between two positive matrices by a family of positive matrices where t is a real number between 0 and 1. And we consider a function f of t, which is the relative entropy between rho and sigma t. So, and that's just given by this difference of traces. I claim that f of 0 and f prime of 0 are 0. And that if, well, first of all, if rho equals sigma, this is trivially 0. I want to prove that it's strictly positive if rho isn't equal to sigma. So I claim that f of 0 and f prime of 0 are 0, and that if rho isn't equal to sigma, then f double prime is positive. So these statements will imply that f of 1 is positive, but f of 1 is the relative entropy that we want to prove to be positive. So all you have to do is prove these statements about the derivatives. Now, these statements are easy, but again, it's a little tricky because they are non-commuting matrices. And if you haven't thought about it before, you might have trouble computing the derivatives. So I'll just make the following remark and leave you to think about it on your own. If you use the same formula for log sigma that we used before, then you'll be able to calculate the derivatives and show that my statements about the derivatives are true. You'll have to think about the operator ordering when you calculate the derivatives. So you'll find it's not completely trivial. It's a good exercise to do if you haven't done it before. And I think I'll stop here. And next time, what I'll do is to describe the Tomita operator and Modular operator in finite dimensions and make contact with Iraqi's definition and then go into some applications. So,
thank you very much.
So maybe there are more questions.
Yes, let's open for questions. Well,
can I ask one question?
Yes,
Yes.
please.
Maybe it's not a very precise question, but in the realm of what we can do in quantum systems, I think we can manipulate quantum systems only with unitary operators.
Yes.
So how do we make contact between these various abstractly defined operators, such as this modular operator, and what we can actually do in experiment?
Well, as I said, I'm going to explain. As I said, I'm going to explain some applications of the formalism we've developed. One will be, well, the new proof by Cassini and Huerta of the C theorem. I only will do it in 2 dimensions, but there are similar stories in 3 and 4 dimensions. Another proof will be to the generalized second law of thermodynamics. So we'll have applications, but it takes more than 1 sentence to, I mean, I can't give a completely instantaneous answer to your question about any application. The classical answer about the relative entropy of an abstract quantum system is that it answers the following question. You're studying a system and you have a hypothesis that the density matrix describing it is sigma, but the correct answer is rho. You're given many copies of a system. After many measurements, how well can you do? How many copies will you need to study before you learn that your hypothesis was wrong? So that's something operational. And if you ask that question, in other words, you don't know what rho is, you only know what sigma is. Your hypothesis is sigma. It happens that the correct answer is rho. Design an optimal experiment on n copies that will show that your hypothesis is wrong, if in fact it is wrong. And how many copies will you need? The answer is that an optimal experiment will show you your hypothesis is wrong once n times s becomes large. While it's easy to say that, it's kind of long to explain why it's true. I wasn't planning to do it in these lectures. I did, well, okay. I attempted to explain it actually in a different set of lecture notes, which I didn't recommend as background for this school because I wasn't planning to do that result. The answer to your question in general, though, is that relative entropy, and you could have asked the same thing about entropy after all. What can we do with entropy? It takes an explanation. Entropy is important in thermodynamics, but it would be a little hard to explain that while standing on 1 foot. So I'd say these quantum things are the same.
Thanks.
I had a question about this example you gave with the differential forms acting on functions that vanish at the boundary.
Yes.
I was a bit confused because the analog that you gave for the d dagger d operator had a parameter t,
Yes.
which was free. It looks like that we defined d, but then we did not fully define the d dagger, and we introduced this arbitrary parameter t.
Well, t, once we introduce t, the operator is no longer d dagger d. The reason I introduced t, well, I could have just told you that the Neumann Laplacian is bigger than the Dirichlet Laplacian, but I wasn't sure if everybody would know that. So I just introduced t to prove that the Dirichlet Laplacian was bigger than the Neumann Laplacian. So I wanted to explain that we can think of the Dirichlet Laplacian
Yes, right here.
as being obtained from the Neumann Laplacian. Sorry, yeah, we can get the Dirichlet Laplacian from the Neumann Laplacian by adding something positive to the energy function. So that was my attempt to explain why it's a more positive operator.
Because so I mean, what's not obvious to me is why this operator should be such that the boundary condition that the function has to vanish comes automatically from minimizing this energy function. It's a bit.
Oh no, it doesn't. Sorry, this one does in the limit as t goes to infinity.
Right. You chose it like that, right? But
Yeah.
In the construction of the operator, we were never.
Well, without introducing t, I would have argued as follows. I think I could have simply claimed that requiring a quantum wave function to vanish on the boundary tends to increase the energy. I think people would have understood that without introducing t. I just introduced t as a way of explaining that fact.
Okay.
Instead of imposing an absolute condition, Reeh-Schlieder corresponds to t equals infinity, but any positive t tends to increase the energy and tends to make the particle avoid the boundary.
Well, okay, I'll think about it. Thank you. More questions?
I have a question about this relative entropy in the QFT case.
Yes.
It was not clear to me if it was already implied by this definition that it's a finite quantity, or is it going to be discussed yet, or is it can it be infinite?
Well, it's free of ultraviolet divergences, but it can be infinite sometimes. It's generically finite. It's free of ultraviolet divergences and therefore generically finite. Let's just look at the case in finite dimensional quantum mechanics. I haven't yet proved the two formulas are equivalent, but we will tomorrow. But if we look at the definition in quantum mechanics, you'll see the relative entropy. Okay. Sigma might not be, if sigma is invertible, then this is always finite. But sigma might have 0 eigenvalues, in which case minus log sigma has plus infinity as an eigenvalue. And if rho is non-zero where sigma is 0, then S can be plus infinity. So even in finite dimensional quantum system, relative entropy can be exceptionally infinite. You see, a generic sigma is invertible.
So you're worried. So if you come back to the definition that you gave, so in that case there was this delta operator, and I was since you did not explain if that operator is bounded, I guess it's not bounded.
No, I proved delta was not bounded, or at least I explained it.
Delta was not bounded. So I was worried more about delta being not bounded, but you're saying the main thing one should worry about is whether delta can have some 0 eigenvalues.
No, well, sorry. I haven't explained yet the relation between delta and density matrices.
Yeah.
Which we'll do next time.
Okay.
So I think I do think the problem is negative, small eigenvalues of delta, because we have the matrix element of minus log delta. So we prove relative entropy is non-negative, so it never goes to minus infinity. The only thing it could do is to go to plus infinity. And to make minus log delta go to plus infinity would come from small eigenvalues of delta.
Okay.
I proved that delta had very large eigenvalues by saying that on a state that's almost an annihilation operator. If you take an A, which is almost an annihilation operator, so A dagger is almost a creation operator, on that state, delta is very small. But conversely, very large, sorry. Conversely, if you act with delta on A on the vacuum where A is almost a creation operator, then delta is very small. The argument I used to prove that delta has very large eigenvalues could have been reversed to prove it has very small eigenvalues.
Okay, yeah, I guess it's fine for me for the moment.
But I want to make contact with something I said to Zohar. So if sigma has 0 eigenvalues, that means according to your hypothesis, you know for certain some measurement outcome that's impossible. And if you get that measurement outcome even once, you know your hypothesis is wrong. So 0 eigenvalues of sigma are relevant in the question of how long it will take to learn that your hypothesis is wrong if it is in fact wrong.
Thank you.
Sure.
Okay, if there are no further questions, let's thank Edward again.
Sure. See you all tomorrow.
And we will continue tomorrow. Well, there is a talk today in 40 minutes by David Samuelsdagen. So let's take a break and return in 40 minutes. See you.